picking up where we left off, we have already seen how to go from grams to moles, and in the next problem we're going to see the opposite. We're going to look from the number of moles, and we're going to figure out what the mass of that would be, or how many grams that would be. So we've already found our molar mass to be 16.042, and that's our conversion factor to go back and forth between grams and moles. So it doesn't matter which one we're starting with, we're still going to use the molar mass. In the example we already saw, we had to divide by the molar mass, but if we're going the other way, we have to do the opposite, which is multiplying. So if we're going to go from moles to grams, like it's asking us in this question to go from 12.2 moles of CH4, and we want to find mass, then we're going to go the opposite way around from this flowchart to remind us of what we need to do. Starting from moles to go to grams, we're going to have to multiply by the molar mass. And I'm going to write that out so you can actually see how our units are going to cancel. If we have 12.2 mole CH4, and we want to multiply by our molar mass, that is 16.042 grams in 1 mole. And just like we've seen over and over again, our units cancel if we have one of that unit in the numerator and one of that unit in the denominator in this type of dimensional analysis or unit conversion. So our moles cancel out and we're left with grams. So essentially, since this is just 1 in the denominator, we just take 12.2 and multiply by 16.042. And times 16.042 gives me 195.7124. But obviously that's too many significant figures, so we need to go down to 3 significant figures. So 195.7 ... We'll just keep going. This would turn into 196 grams of CH4 in 12.2 moles. Okay. Alright, so we can also use this flowchart to remind us of how to do conversions between moles and particles. So we're starting out with 1.5 times 10 to the 24th molecules, and it's asking us how many moles this is. We're going to go in the direction from particles. We're starting out with the particles, the molecules, and we need to go to moles. And that tells us that we need to divide, which makes sense, because that means we're going to take the number of molecules we're given and divide by the number of molecules in a mole. So that would be 1.50 times 10 to the 24th molecules. And if we're dividing, that's the same thing as putting it in the denominator. 6.022 times 10 to the 23rd molecules are the number of molecules in 1 mole. So here's basically our conversion factor, and molecules will cancel out in the numerator and the denominator, and we'll be left with moles. So let me divide that on my calculator. 1.50 times 10 to the 24th power, divide by 6.022 times 10 to the 23rd. And I'm getting 2.5, or 2.49 with correct significant figures. 2.49 moles. Okay, so this kind of makes sense because if you look at our exponent, this 24th is only one place value higher, so that's basically like taking 15 and dividing it by 6. And that's one way to think about it as to why we got this answer. Okay. All right. So one last thing we should look at is thinking about the mass of the percent of our mass that is made up of a certain substance. So any kind of percent, I think I've mentioned this lots of times, any kind of percent you'll calculate by taking the stuff that you are trying to find the percent of and putting that amount in your numerator, and then whatever you're trying to compare it to what it's a percent of what. That's the entire thing. Will go in the denominator. So, for example, if I wanted to find out what's the percent off for a sale, then I would take the amount that has been deducted from the initial price, and that amount that had been deducted would be my numerator, and the initial price would be my denominator, because that would have been the entire original price, and now I want to know just how much has been taken off, which is the stuff I'm interested in. So here's an example. If my sister's dog weighs 42 pounds and 23 of those pounds are from water, what percent of the body weight is from water? So what part are we interested in? We're interested in the part that is made up of water. And so the weight of water in this question is only the 23 pounds. So the 23 pounds is the stuff we're interested in. It's going to go in the numerator. The whole thing is the mass of the whole dog. So the mass of the whole dog is the 42 pounds. I totally made this up. I don't know what the weight ratios for animals and water are. But the last thing we have to do for any percent is multiply by 100. You can probably tell it's going to be about 50%. But let's see. 23 divided by 42 times 100 gives me 55%, if I round to two significant figures, just like these numbers here have two significant figures. Okay, 55% water. Okay, now if we wanted to think about water itself and be able to figure out what percent of the mass of water is oxygen, we need to find the whole thing, and we need to find the stuff we're interested in. So what stuff are we interested in? Are we interested in the hydrogen? No, it's asking us what percent is the oxygen. So in order to do that, we need to know the mass of water. We need to know the mass of oxygen. Water we calculated a little bit ago to have a mass of 18 because it's got 2 hydrogens times a mass of about 1, and it's got 1 oxygen with a mass of about 16. So that gives us a total of 18 grams per mole of water. The mass of just oxygen itself is 16 grams per mole. So let's take the stuff we're interested in, divide it by the whole thing, and multiply by 100. So that would be 16 divided by 18 times 100, and it should be pretty close to 1. I've got 89%. 89% oxygen. That's an O. So 89% of the mass of water is oxygen. Alright, so let's review everything together. If I was to buy a container of salt from the store, and the container, I put it on the scale in the lab and found that it weighs 217 grams, we want to know how many molecules of sodium chloride, which is the same thing as salt, are in our container. Let's ignore the container itself. Let's pretend it doesn't matter. I could have dumped it all out onto the scale. Alright, so I've got an initial amount of grams, and I want to go all the way to molecules. Now I can't just go directly from grams to molecules. I have to go and follow, this flowchart's a really good reminder. The process is our grams, we have to first convert them to moles, and then moles has a conversion factor to take us all the way to molecules. So let's start with our grams. We were given 217 grams. So 217 grams, what am I going to need to convert my grams to moles? Well, if we remember, we're going this way from grams to moles, we're going to need to find our molar mass so we can divide by our molar mass. So that means we want to know how many grams are in 1 mole NaCl. We can calculate that pretty easily using their masses from the periodic table. So sodium weighs 22.99 and chlorine weighs 35.45. And so if we add those together, we're going to get 58.44, I think. Yes. 58.44. Okay, grams per mole. Right? So in my denominator here, to make it a division process, I'm going to put my 58.44 grams. All right. So now we got to divide 217 by 58.44 to find how many moles of NaCl. I've got 3.71 mole NaCl. And the last step here is to go from moles to particles because we are asked how many molecules. Okay, so that's the final unit we have to reach. Okay, so to go from moles to molecules, I'm going to have to multiply by Avogadro's number, 6.02 times 10 to the 23rd power. And that's how many molecules are in 1 mole. So my moles will cancel when I'm multiplying by Avogadro's number, and I'll end up with the number of molecules. So this number, 3.71 times 6.02, 2 times 10 to the 23rd, I've got 2.24 times 10 to the 24th molecules. Alright, so that would be my final answer for the first question here. Now I want to know what percent of the total mass is sodium. We could either use the mass of the container, or we could just know that sodium is always going to have a constant percent out of whatever is sodium chloride. So we can just take the information we've already broken down up at the top for our molar mass and use that to calculate the total mass percent that is coming from sodium. So the part that we're interested in is not the chlorine. The part that we're interested in is the sodium. So we're going to put that in the numerator, 22.99 grams. And then our denominator is not going to have the chlorine. It's going to have the whole molecule because the total mass is talking about the whole thing, which is sodium chloride, 58.44 grams. So we divide that and multiply by 100, and that will give us our percent of sodium. Alright, so I've got 39.34% if we're using significant figures. Remember, we can ignore the 100 because that's just there to change the place value. So this is the percent of sodium in sodium chloride. Forgot to mention that. All right, and that is all we have for today. So if you have any questions after watching this video, make sure you write those down and bring those to me because this is going to take us a while to make sure we understand how to do these calculations. And if you read a more complex question, make sure you know how to answer it. But a flowchart like this is very useful, but you cannot expect that you would have something like this on a test. So you really need to understand why we use molar mass to go between grams and moles, and why we use Avogadro's number to go between moles and particles. All right, that's all we got.